All right, so in our last video, then we determined that there's a certain way for us to write numbers based on the tools that we used and the measurements we took, right? So in the first example we looked at, we had like our ruler, and we saw that when, here's our graduations, whenever something fell in between the graduations, we were able to estimate one place passed. So I think we came up with our measurement of like 9.57 centimeters on our ruler. We came up with, I believe it was like 18.4 milliliters on our short graduated cylinder and 60.0 milliliters on our large graduated cylinder. And so what this does is the way we've written the numbers shows a certain number of confidence, or shows a certain degree of confidence. And the reason that we have to write these numbers this particular way based on our measurement is so we can communicate our certainty. And the way we communicate our certainty in numbers is through something called significant figures. And significant figures reflect the confidence we have in our measurements. So whenever I look at a number, there are going to be some parts of the number that are significant, meaning they show certainty, some parts of the number that aren't significant, meaning they only act as placeholders. And so what there's a set of rules that's going to help us figure that out. So what I'm going to do is I'm going to outline the rules for you, and then we'll take a look at the examples we measured, determine the number of significant figures, and then continue with some additional examples. So in this case, we're going to look at rules to see if a number is significant. Or if it's just a placeholder. So in this case, remember, significant means confidence. Placeholder means just there to make sure we're in the right spot. So when we take a look at our 9.57 centimeters, we see that all of our digits are not zeros. And so anytime I see a digit that's not a zero, that digit is significant. And so then that kind of says, well, what happens if I have a zero in between two non-zeros? So like 101, for example. So any zero between two non-zeros are significant. From here, we're then asked about, start looking at our zeros. So in this case, I have two scenarios. I can see that I have a zero at the end of a number, like up here, or I can have a zero before a number, and I'll show you an example here. But any leading zero, or a zero in front, is not significant So for example, if I had 0.00685, since I have these three zeros, they're not showing how confident I am in my measurement, they're just showing the place. So I would only count 3 significant figures in that number because they're in front. The last situation that I can have is like in our 60.0, where I have a trailing 0. And in this case, a trailing 0, so 0's at the end, is significant only if there's a decimal point. So let's take a look at some examples keeping these rules in mind. What we're going to do is we're going to look at a measurement and we're going to determine the number of significant digits in each measurement. So if I give 3.14156, if I were to give 4.0085, if I were to give 0.0000855, if I were to give 100.700, and we'll do one more. Let's say I had 150,000. So what we're going to do is we're going to take a look at our rules and we're going to determine the number of significant figures in each measurement. So when I take a look at this first one, I measured 3.14156 units. None of these are a 0, so according to rule number 1, I have 6 significant figures in this number. When I look at this next example, I have 1, 2, 3, 4, 5 digits, and 1, 2, 3 of them are not 0, but both of these zeros are in between a 4 and an 8. As a result, that means because of rule 2, I'll have 5 significant figures. Looking at the next one, I have a whole bunch of zeros in front of a non-zero digit. So I have a bunch of leading zeros, which means all of these don't count. So that means I have 1, 2, 3 significant figures inside the measurement. Following my rules on my next one, I see I have 2 non-zeros, a couple in between, so all of these are significant. But the question is, what about these guys? In this case, I have zeros at the end, and I do see a decimal point. So according to rule 4, I would say that there are 6 significant figures here. Conversely, I'll see a similar rule have to be applied here in my last example. With 150,000, I have 2 digits that are not 0, so they're automatically significant. These last 4 zeros are not significant. And the reason they're not significant is because there's no decimal point. So I would say that there are 2 significant figures. Now, one thing that my students always get confused on is if a 0 isn't significant, do I have to write it? And the answer is yes. So in this case, if I were to look at this last example here, my 150,000, and I rewrote this as without the zeros, these numbers are no longer the same. So I still have to write my zeros even if they're not significant. Same thing on the third example we did, where I had my 0.12345855. if I wrote that out as 855, that's not the same thing. That's off by a really, really big magnitude. So make sure that even if a zero is not significant, that you're still writing out the zeros. All right, so now that we've talked a little bit about significant figures, and even though they're not significant, you have to write them, all those other good pieces, let's take a look at what we can do once we've collected these measurements, right? Because when we're taking a look at our first, kind of one of our first big topics, we're going to be looking at something called density. And what density tells me is how much mass and how much volume. So effectively, how much matter did I cram into a particular space? So this should look pretty familiar from like a physical science class you might have had, where density equals mass divided by volume. So in this case, you just plug stuff in, and it's really easy to do. Some important pieces about density. You'll always have 2 units. Some common units that you might see are grams per milliliter, kilograms per liter, grams per cubic centimeter. You also might see grams per cc, but in this case, grams per mil is the same thing as grams per cubic centimeter is the same thing as grams per cc, and that's because 1 milliliter is the same thing as a cubic centimeter, and cubic centimeter is abbreviated as cc. So it all ends up being the same. But in this case, you'll always notice you have some kind of mass unit in the numerator and some kind of volume unit in the denominator. And this is pretty important because in our first experiment in lab next week, we're going to be taking a look at a technique called volume by difference. So we're going to be taking a look at some mathematical operations with our measurements. So what I'm going to do is I'm going to describe a quick experiment for you. What you'll be doing next week in lab is you'll be given a series of cylinders. And these cylinders will all be made out of the same material, but they'll be different sizes. And you're going to take some measurements of the mass and volume of each cylinder to determine your density. So we're going to do a quick example. Let's say I have a cylinder and I record the mass of this cylinder to be 81.38 grams on my digital balance, and I determine the volume using a technique called displacement. So in displacement, what happens is I take a graduated cylinder and I've got some water in the bottom. What I'll do is I'll take my object my rod, drop it in, and what should happen is the water level should go up. And the change in volume of the water is the same as the volume of the object. So let's say my initial water line had a volume of 20.0 milliliters, and when I added my object in, the volume of the water and the object came out to be 25.7 milliliters. We have to do 2 different operations here. We have to do a subtraction operation and then a division operation. So what I'm going to do is I'm going to line up my units, my 25.7 minus 20.0. And so what I'm going to do is I'm going to draw a little line after the last place that they have in common so that they both end in the tenths. So That makes it pretty easy, and I end up with 5.7 milliliters as the volume of my cylinder. So in this case, whenever I did an addition and a subtraction, I ended up lining up the decimals and then I rounded to the nearest common place. Let's call that last common place. And so now, when my measurement started, I had 3 significant figures in each measurement, but the difference between the two ended me up with 2. So it's very possible that you can see the number of significant figures you have change during an addition and subtraction setup. The second potential set of operations you can see is a multiplication and division. And in this case, I round to the lower number of sig figs. So when I go to calculate my density, I take my density of 81.38 grams and I divide it by my 5.7 milliliters. And so when I type this into my calculator, what I end up with is 81.38 divided by 5.7 milliliters. And this brings me to a density of 14.2772. And my units are grams per milliliter, because I have grams up top and milliliters on the bottom. But now, when I take a look at how many significant figures I should have, I count 1, 2, 3, 4 on top and 2 on the bottom. So what I'm going to do is I'm going to go over 1 to my second significant figure from the highest place, and I look over here at the next number. If it's 0.5 or less, I round down. 0.4, less than 0.5, I round down. 0.5 or greater, I round up, and I come out to 14 grams per milliliter as the density reported to the correct number of significant figures. So as you're going through this, be aware and using your measurements to help you calculate physical properties, calculate other pieces of data. Be aware that you're sometimes going to run into these significant figures in terms of calculations. So make sure your measurements are really clean so you can help maintain the most significant figures in your answers.